Hello all, my name is Lars, and today I'd like to present Cbnav, a custom map-based approach to deep reinforcement learning mobile robot navigation. Professor Eduardo Todd oriented this research. Mobile robots must move from an aleatory start point to a not previously targeted position. In most cases, the minimal capability to move is not enough or present an acceptable span of energy and time that makes this task unfeasible. Through the years, different approaches have been used to solve this task. The most common method is based on environment map construction. So the map can be constructed online, as pressed by SLAM concepts, or supplied to some navigation algorithms when the map is known a priori. Despite the success of using map, this approach still requires extensive effort before they can work reliably in the real world. And more eloquent than it, the solution is not generalized due to the map. So we need to create a map to one specific environment, and the robot will navigate only in this environment. In nature, some animals and bugs have a different approach to navigate in the environment. For example, sniffing in lobsters, whisking in rats, and antenna mediated in cockroaches are examples of sensors used to navigate. The information is used to both sensor measurement adaptation and propagation through neural feedback control. Concerning the example of cockroaches here, the musculoskeletal system is adapted to not touch the hull and move near the obstacle. So the first time, state number 1, the cockroach touched the hull, so the antenna mediated is adapted to measure the distance between the musculoskeletal and move near to the hull without touching the hull. Complementary to free collision techniques, ants use pheromone-based navigation to create a safe path from starting to the target position. For example, the trajectory path was created by one ant, and all the ants can move in the same path, just following this previous path created based on pheromone-based navigation. In summary, bugs do not know the environment map, but know how to navigate through the environment without collision, making start and target locations each time. To replicate the navigation techniques, research based on deep reinforcement learning and recurrent neural networks are used. The most basic approach to reward an action is to measure the angular displacement and linear distance between the robot base and the target position. Again, values are applied and the result in SI gain value. So the linear displacement and angular displacement can be measured. Alpha and beta can be applied to generate again to linear or angular displacement. Each action results in a new state data. If it's not a finalization state, the calculated reward is applied. This kind of reward function works fine to the conjunction present by the picture. For example, here we have the base of robot and the target. So in this case, to maximize the reward function, we will turn the robot counterclockwise and move forward. We will reduce the distance, linear distance, and we will reduce the angular distance from robot to target position. However, concerning conditions present by both pictures, the reward function will increase if the robot turns clockwise and move forward. What's not defined path due to the hull. So in this case, if we try to maximize the reward function, we will touch the hull because we will turn clockwise and move forward. In order to mitigate this behavior, we propose the cost map reward function and cost map path function. Cf is a height matrix to describe where are the most promising places to navigate inside the environment. The matrix involves with training episodes as illustrated by pictures. So here we can see in the first episodes, it's this very simple custom reward function. Every yellow part of the matrix represents a place to not be. With the evolution of the number of training episodes, it's identified new positions to be, as can be observed in red one. Only the not good place to be is the yellow places near to the house. Cpf is a matrix as well, where only the episode path is stored. In this case, we are trying to replicate the pheromone-based navigation. Cpf is necessary to motivate the robot to not pass through the same path. If it occurs, the discount factor D is applied. So here we have the Cpf matrix create for each episode. If the robot passes through the same position where he already passed, so the discount factor is applied and the reward function receives a discount. The reward function is used in dwelling double deep key learning network training process. Here is the function ROI. Okay. The models N1 and N2 were created. N1 represents the baseline reward function, and N2 with CRF and CPF reward function. 5 environments were created, and both networks are trained in these environments, generating 10 models, N1, 2, and 10. It was evaluated every model concerning 5 environments 10 times, 1,000 tries each time, generating 10,000 tries for each model. It was measured the average of the number of times the target position was reached. And the null hypothesis is CRF and CPF do not increase the number of reached target position. And as usual, the confidence interval is 95%. Here we have the results. Both tables present the average for each test, and the graph represents the hypothesis results. As you can observe here, it's only the average of all the 10 averages for each model, and the average calculated for all 5 environments for each model, and also the standard deviation. And here we can see the results. Every result less than 0.05 represents the possible to reject the null hypothesis, or CPF and CRF increase the number of reached target position. Only for environment number 3, it was not possible to be observed. As a conclusion, we can say Cbnav increase model generalization, because here, for example, we have model. Here we have the model trained in environment number 1, but applying the model trained in environment number 1, we could navigate well in environment number 2, 3, 4, or 5, in 5. It's the generalization we are trying to apply. Environment complexity matrix must be established. For example, we don't know how the environment number 3 was the only one that not present significant results. It's probably because it's the most simple environment created. But to investigate and to create a new hypothesis, we need to measure the level of complexity of each environment. So we are already working on a complex matrix to measure any numbers of new environments. and the number of environments will be increasing in a new evaluation of the Cbnav. All the results, all the code we can find here, and this is my personal code. Thank you for watching. See you.